half-wave rectification. Now, before we start, first is, what is the characteristic of your AC current? Let's say we have an AC current. What is so special about AC? How is AC different than DC? Okay, first thing is that the magnitude of AC is different over time, right? It changes, it rises, drops, and then rises, drops, rises, drops. And second, this is positive, this is negative. So every half cycle, the current will switch direction. First half cycle, it is positive, the magnitude changes. The second half cycle, it goes below, so it changes direction. That is the behavior of the AC. Is it useful? Is it useful, this behavior? The question is, it depends. But if you want to charge your battery, let's say your laptop battery or your phone battery, we don't use AC. AC cannot charge a battery. Okay, for all the rechargeable battery, it cannot work if you supply AC current. Because to charge a device, to charge a battery, inside the device got a capacitor. And if you want to charge the capacitor, you must supply AC. If you supply DC, then it charges the plate. This one becomes positive. And then when the AC switch direction, this one becomes positive. So this will discharge the capacitor. What is the function of a capacitor? Capacitor 用来做什么的？ Capacitor 是用来 store charge 的 ，store charge。所以如果你用 connect 它去 AC 啊，它 store it cannot because it will charge the capacitor, it will discharge again. It will charge and discharge, so it's like nothing happened. Only DC can work. Okay. Now, other than rechargeable battery, AC is also not useful in chemical process like electrolysis. Electrolysis, remember you learned in chemistry, you have the two electrodes, right? And then we use it to separate the molecules of water. We can separate oxygen, we can separate hydrogen by having the positive and negative electrodes. That is, what is the power supply? The power supply is DC. If this is positive, this is negative. That is DC, already fixed. If you use AC, meaning that this is positive, this is negative, then this becomes positive, this becomes negative. The terminal, the positive and negative terminal keep changing because of the AC current keeps changing direction. So does it work in electrolysis? If you use AC current, electrolysis also doesn't work. Okay? AC current only useful in where? Only useful in transformer. Okay? So when I want to step up, I want to increase the voltage or I want to decrease the voltage, I use a transformer. And that only works if I have a DC. Sorry, if I have an AC. Okay? Because you need changing magnetic field and then it will produce induced current. That is the only use of AC. So meaning that all the devices you have, your iPhone, your phone, your Android phone, your smartphone, anything, your tablet, your desktop, your laptop, all powered by DC. All powered by what? DC. But your socket, you connect to what? You connect the home socket, right? That is DC. Sorry, that is AC. AC is coming from the adapter. Inside, they have to convert it. They have to convert it to DC, only that the DC goes to your laptop battery. Okay? So the process of converting the AC from the socket to DC until it reaches the battery of your device, that process of converting, we call it rectification. Okay? So rectification is I change AC current to DC current. So from here, this is the graph of the AC. If I change it, I rectify. I want to make it become what? I want to make it become steady current. Straight line is not changing, magnitude is not changing. So I want to change it to steady current. Only steady current is useful, especially if you want to charge rechargeable battery. Any rechargeable battery, they works on steady current. But there's another question. Once you change it to steady current, can you go back? Cannot. Okay. Once you change it to steady current, also the magnitude of the current, you cannot change back already. What is the supply of AC? When you plug in the socket, it's giving you 240 volt. Okay. When you change it to steady current, let's say you change it to 50 volt. Then 50 volt, you cannot make any changes to the voltage anymore. It has to be 50 volt fixed. If you say, okay, I want to increase a bit, I want to make it 60, cannot already. Because once you rectify, it cannot go back. This is very important because means that before I want to change it to DC current, okay, before I rectify it, I have to use a transformer to step it up or down to the voltage I want before I change it, before I rectify it. I repeat, before I rectify the AC to DC, I have to use a transformer to step up or step down to get the voltage I want. Then only I rectify, change it to DC. Because once it is in DC, it cannot go back. You cannot change the voltage anymore. Which is why in rectification circuit, rectifier is a type of circuit. You can see on the diagram here. This is rectifier. Okay, what is a rectifier? Rectifier is a device that converts AC to DC current. This is a type of arrangement. So rectifier is not a device. It is a type of arrangement. This arrangement is rectifier. Okay. Now you can see that this arrangement has a transformer. That explains why first we need to step up or step down first, then only we convert to DC. So the first portion of a rectifier must be a transformer. Okay, not must be, usually it has a transformer, all right? Okay, so you can see on the left side is the AC. So this is supplying AC. This is the input. Okay, this is on the other side is the output over here. If I connect a circuit from this two terminal, CD, to any circuit, okay, this is to your laptop, right? That is the output. Once it goes to CD, that is already DC. How does it work? Okay, let's understand this. Now, to get a rectifier, you can use at least one diode. I place the diode over here and with a resistor, okay, whatever the load here. Excuse me. Okay, now, from the AC output, the first half cycle, current flow in one way. You can look at the graph here. From here to here, it is all positive. The magnitude of the current changes, yes, but the direction is in one way. Let's say that this is positive, this is negative. So the first half cycle, the current flow from positive to negative. It goes from point A to diode 1, and then to resistor, and then to point B. So I can write it here, first half cycle. Okay, what is the current flow? A to D1 to R and then to B. That's clockwise, right? Now, look at this current flow and look at the diode. How is it placed? This is P and this is N, our PN junction. And the current is flowing to the right, which is same direction as the body of the diode. the body of the diode is also pointing to the right. That is what connection, forward bias or reverse bias. This is forward bias. So in the first half cycle, the arrangement is forward bias. What happened in forward bias? Meaning that the current is allowed. Current is allowed to pass and current is allowed to flow through the circuit and comes back. So the first half cycle, there is current flowing. What is the output if I can connect a CRO at the output? Let's say I want to measure the current passing through this resistor. I connect to a CRO. Okay, so CRO, we can displace the wave, the current graph. What graph do I see? Okay, here is the output. The output means whatever is shown on the screen of the CRO. Okay, so this is the graph and it is the same. Rise, magnitude of the current rise and then drops. This is in positive direction. Okay, now let's look at what happened in the next half cycle. From here to here, what happens to the current? The terminal changes, meaning that point A is now negative and point B becomes positive. So the current direction flow changes. Second half cycle. What is the current flow? Starting from B, it flows to R, flows to D1, flows to A, and then goes back into the coil. Okay, B, R, D1, A. Look at the current flow. Compared to the diode, what is the arrangement? Here, the arrangement is now reverse bias. Okay, so for the second half cycle, this connection is a reverse bias. In reverse bias, the resistance become infinite, become very large, and the current become very small, as if there was no current flowing in the circuit. So current is not allowed to flow in the circuit. Meaning that if I connect my CRO between this resistor can be anything. It can be your battery, it can be any load. Okay, I just leave it resistor. Okay, any load. So if I connect the CRO here, what do I see? The waveform. Here, because current is not allowed to pass, so this part of the wave is being canceled out. It's like missing. So here, from here to here is a flat line. No voltage, no current. This can be a IV graph or, IT graph, or it can be a VT graph. Normally, more commonly is VT graph. Okay, VT graph. Voltage over time. This is the output of the CRO. Input, you have the negative region here. Now, comes to the next half cycle. The next half cycle becomes the same as the first half cycle, meaning that everything repeats. Current is allowed to flow again. Increases, magnitude reaches the peak, drops, and then goes to the next cycle. Again, current is not allowed to pass through. So I get on my CRO, what do I see? I see that this is like on and off, on and off, on and off, on and off, like this. Okay, now, of course, amplitude must be the same as the amplitude before. Only the negative part of the wave is missing. Now, how do I describe this current here? This is the current passing through where? Passing through resistor R, correct? Yes. Or anything that you connect between terminal C and terminal D. You can even branch out another circuit. Okay, connect CD, 做另外一个 circuit. 可是那一个 circuit 全部的 current 都是跟着这一个 output current 这样子 flow， 就是 increase current, no current, increase current, no current. This one we call it unidirectional. Unidirectional, uni one, directional, one direction. It's flowing in one direction. And how is the property? How does it behave? It's like this. Increase, drops. Increase, drops. Increase, drops. Okay? So is this useful? You see, half of the energy is wasted. I input how much energy? This much. The AC current. Now coming out, only the top part. 50% gone already. 50% of the energy is wasted. Okay? So this is not a popular rectifier because this rectifier eliminates 50% of the energy, and we don't want this. In practical, we don't use this. It's useless. Okay? So we have another type of rectification, another type of rectifier. Okay? But the question is, how do we improve it? If I want the missing part, okay, I want the missing part. I don't want my current to be like on and off, on and off. That is, you cannot use anywhere. You connect to a circuit, suddenly got current, suddenly don't have current. We don't want that. So we want unidirectional, that is DC, okay? We want it to be unidirectional. At the same time, we want the voltage always there, not on and off. Okay, we want the voltage to maintain there. That is why we have another type of circuit. We call it the full wave rectification. So this is half wave because only half of it is being remain. We call it half wave rectification. Okay, now let's go to the next one. We look at full wave rectification. I will go to the next slide. Okay, full wave rectification. Full wave rectification, you can see the circuit is a little bit different. Actually, it's the same, just that we added one more diode. So I got two diodes and I add another branch in the middle. Okay, now let me explain. Why do I make another branch here? Point C, you can see point C, I branched out from this coil of wire. This is coil of wire transformer. Now, we are not going to talk about how the transformer changes the voltage. That is for the transformer one. Today, we focus on the rectification. So you see, this terminal C, I branched out, meaning that between A and C, there is a potential difference. Between C and B, there's also potential difference. Now, the way you understand it is like this. Imagine like you have wire. Okay, 有一条 wire, and then terminal A, terminal B. 如果我讲 current 是 flow 去右边，哪里是 high potential? Current 永远是 flow 从 high potential 去 low potential. 所以 point A 会是 high potential, point B 会是 low potential. 然后如果我去 connect 多一个 wire 在中间拉出来，这个我叫 point C。C 是 high potential than B, but lower potential than A. Because when current flow to the right, the potential decreases. What is the use of this? If I branch out like this, then I can connect whatever circuit I want. I will have a potential difference of AC. Same here, I can connect to any circuit I want. I would have a potential difference of BC. So current will flow in any of the circuit. Okay, so this is the same as this diagram here. This is the coil starting from A, flowing down. A has a higher potential. If I make this as positive, and I make this as negative, so current will flow from A to B. Which one has a higher potential? A highest potential, C, and then followed by B. Okay, now let's stop for a few seconds and see who is lagging. I mean, can you hear me? Give me some sign. If you can hear me, you give me a thumbs up. If you can hear me well. Oops. Okay, Ashley can, Dylan can. Ariel can. All right, thank you, thank you. Because I keep seeing the internet connection pop up. Okay, we'll continue. All right, so now 3个 terminal， 然后每个 terminal 不同 potential difference. So meaning that there is current flowing in it. Okay, now let's see how it works here. My input current is AC, right? So it looks like this. AC is like a sine wave, sine graph. On the right side of the circuit, this side, it becomes like this. Okay, now how do I get this graph? Okay, see, first half cycle, we draw it like this. First half cycle from here to here, current flow clockwise. So A is positive, B is negative. Current flow from A to D1 and then to point M. And then here, PQ, let's say I connect a resistor. Can be any resistor, resistance R. Okay, then the current stop at, when the current arrives at point M, what happened to the current? You see, there are two ways that the current can go. It can go in here or it can go down here, right? When it reaches point M. Where will it choose? Bottom, you can see that if it chooses to go bottom, then it will be in a reverse bias, meaning that the diode will prevent it from going in this direction. Do the current just stop at M? No, charges, when they flow, they don't just stop. They will find alternative. They will find another way. So they will choose to go through the PQ, go here. And the reason why they can flow inside here is because the terminal C has a lower potential than terminal A. So higher flow to lower. If terminal C has a higher potential, then it cannot flow in that branch. You have to always make sure current flow from high potential to low potential. So the current can go in here, in the middle branch. So current flow A to D1 to M to P and then to Q and then to C and then back to B. Okay, like this. Now, this is first half cycle. So the output graph, I get same as the first half, like this. Second half, from here to here, the current changes direction, meaning that now A become negative and B become positive. So current start to flow from where? From point B. Okay, from point B, and the second half current flow from B to D2 and then to M. Can it go to D1? No, because D1, the diode will be in a reverse bias. Current reaches point M. From D, it reaches point M. It cannot go to the top. It can only enter this branch. Okay, can only enter this branch, and so the flow become M, P, Q, and back to C again. Now, focus on the two paths, the path of the current. Here, in the middle branch, current go from P to Q, right? And here, the first half, it goes from P to Q. The second half, also the current flows from P to Q. That is same direction. The third half, same, also from P to Q, meaning that the direction of the current in the middle branch, never changes. It goes from right to left. Okay, so if I want to plot the output graph, I connect my CO. Where do I connect my CO? This one is very important. If you connect your CO here, sorry, CRO, you connect your CRO here, what do you get? You get the sinusoidal graph, the sine graph, because you are reading the AC. If you connect your CRO here, here and here, let's say around the diode, what graph do you get? If you connect the CRO between the D1, what graph do you see? Because the diode only allow current to flow in one direction, right? So the other direction is missing. What do you get? You get like the first graph we have for the half-wave rectification. On and off, on and off. If you connect to the diode down here, you get the same thing. On and off, on and off, on and off. But if you connect to the center branch, CRO, then you get graph like this. First half, voltage, positive. Second half, again, voltage positive. Third half, positive. Fourth half, positive. It's like we have flipped the graph from negative, I flip it up. Okay, because first half, second half, also there is current flowing. Current flowing from where to where? From P to Q, from P to Q. That's why you get the graph like this. Rises, maximum amplitude, increase. Drop, rises, drop, rises, drop. So this graph shows full wave because I am able to retain 100% of the input current as the output current. And what have I changed here? I have changed the direction. This is unidirection. What about the magnitude? Have I changed the magnitude? I did not change the magnitude. And that comes to the second question. Can I change the magnitude? Because yes, it is in unidirection, that is good, but still the magnitude increase and fall, increase and fall, increase and fall. We don't want this. We want to get what? At the end, we want to get steady current, not changing. So how do we go about this? How do we go about this? So far, we have rectified what? We have rectified the direction. Now we want to rectify the magnitude. Okay, now then I need to make a little bit of adjustment. Now, see, okay, I will erase this. I will erase this. If you want to take a screenshot, you can take a screenshot. I will erase this and we do a little bit of adjustment to the current circuit. We still use the same circuit. We change a little bit things. Okay, now what do we want to do now? Our main purpose is to maintain the direction, but we want to rectify the magnitude to get a steady current, right? To get a steady current. We don't want this like bumpy, this bumpy current. Okay, now what I do is between this PQ junction, I connect to another circuit. That is, we call it the filter circuit. Let me draw it like this. Here, I connect this to terminal P, terminal Q, and I connect this to terminal P. This symbol is just to show that they are not connected. Okay, the wire, they are not connected. So here. Now, I branch up another circuit, a minor circuit, and then I connect a capacitor. This is a capacitor, and beside the capacitor, I connect to a high resistance resistor. This is high resistance. Later, I'll explain why, okay? And then continue to the output. This is to output. Yeah, now this is the circuit I connect. What is the function of capacitor? Capacitor is used to store charges, right? It is found in your power bank. Store current, store charges. Okay, and then you use it to charge your device. So the main function of the capacitor is to store charges. When the charges goes to the capacitor, it will stuck there, it will accumulate there, and when needed, it will release the charge. Supply temporary current. Okay, that's capacitor. Now, here, let's say that, okay, let's observe what is the current direction. From here, look at the graph. From here to the peak voltage, current flowing in one direction. And if I take A as my positive, B is negative, then the current flow in clockwise, right? Clockwise means when it comes to PQ, the current flow from P to Q, okay? A to D to M, and then to P to Q. So it's going from P to Q. That is the first half. Meaning that inside this circuit, it is flowing here through the capacitor, through the resistor, and through whatever output circuit here. And then eventually it has to exit from the Q here. Okay? Now look at the magnitude of the current. The current flowing through this branch of wire, this P here, it keeps rising and falling, right? Because you can see the graph from 0 to, okay, let's say this is 10 volt. The current flowing in the P through the wire, from 0 increases to 10 and then drops to 0. Increase to 10, drops to 0. That is based on the graph, right? Now, when the current increases to 10 volt, the current will go into the capacitor and then it will charge the capacitor. Okay, it will charge the capacitor. So all the charges will stuck here. This current, this wire is supplying 10 volt. So meaning that it will charge the capacitor with 10 volt as well. And at the same time, also 10 volt will go here through the resistor and through to the output. What happened when the current in the wire drops to 0? The next second, it goes from 0 to 10 volt and it drops to 0 again. When the current drops to 0, then who is supplying the 10 volt right now? The capacitor will supply the 10 volt. Okay, the capacitor, the charges will be discharged. When I say discharge, it means that the capacitor is supplying the current. Okay, discharge. Discharging a capacitor, the capacitor is supplying the current temporarily. It is giving the 10 volt. So when the supply becomes 0 volt, Then the capacitor release the charge to the output circuit, and the capacitor now is the one that is giving the 10 volt. But it cannot give the 10 volt forever, because it can only give the amount of charges, the maximum charges that it stores, right? Eventually it's going to come down. When it discharges, the voltage will drop. This is just temporarily. Okay, you see, huh? Now, the capacitor discharged from 10 volt. So meaning that it's giving 10 volt, and then 9.8, 9.7, 9.6, 9.5. By the time it drops to 9.5 volt, the supply comes back. What supply? The supply flowing, the current flowing in the wire P comes back, because it goes 0, increase to 10 volt, and then drops to 0, and then it comes back again, increase to 10 volt, and it will push the current all the way back to 10 volt. Then again, we have another 10 volt coming. Okay, so the 10 volt is going to the output again. Again, repeat. The current drops to 0. Who is supplying the 10 volt? The capacitor is supplying the 10 volt until the next supply comes in to push it way back to 10 volt. So meaning that every time the supply drops to 0, the capacitor is doing the job of giving the 10 volt until the supply comes back. Okay, huh? So meaning that at the output, if I connect the output to a CRO, this CRO will always receive what? It will always receive between 10 volt and 9.5. It will never receive current that is below 9.5. Why? Because when this drops to 0, the capacitor is holding, is giving 10, 9.8, 9.7, 9.6, 9.5, not below it, and then the supply comes back. So the lowest that it can receive is 9.5. Meaning that any load, any devices you connect here, the voltage is, the supply of voltage is between this range. Most importantly, we have to make sure the capacitor discharging time, meaning that how long it takes the capacitor to discharge, must be longer. Discharging time must be longer than the cycle. Then here, okay, this is 10 volt, right? Where is the next 10 volt? Here. Here is supply 10 volt, it drops to 0, rises again, supply another 10 volt. Meaning that the capacitor has to do the job between this duration, right? Whatever the duration here, the time between the first crest to the next crest, the first maximum to the next maximum. This time, this duration is when the supply is not at 10 volt. So the capacitor discharge must be longer than this one so that the next 10 volt will come back. Okay, I repeat, the capacitor start discharging when the graph from here drops. 10 volt, as soon as it drops, the capacitor start doing the job, discharge, give the charge, supply the 10 volt. And then it has to hold until this comes back. So meaning that the discharging time must be greater than this T. Okay, this is like the water tank in your house. Our overhead water tank. In the morning, you use the water. Then the water level in the water tank, 10 meter drops to 9.8, 9.7, 9.6, 9.5. In the evening, the supply of the water comes back and top up the tank. rise back to 10 meter. In the night, you keep using the water, drops again, 9.9, 9.8, 9.7, 9.6, 9.5. The next day, in the evening, you get water supply again, top up. So, meaning that the water level will never drop below 9.5, right? It is always between 10 and 9.5. It will never be empty. That works the same way as this one, the capacitor discharging, meaning that you will never experience the bottom region of the graph. At the output, the bottom region of the graph will not be seen. It will not be experienced. Only the top region of the graph. Okay, so meaning that I can draw my output like this. If I erase this, okay. Now, with the capacitor connected in the circuit, this is the 10 volt, right? The moment it drops, capacitor is supplying. So the capacitor supplied this smoothen. It smoothen the graph. You can see I draw a straight line joining to the next mountain here, right? So without the capacitor, it would drop like this, drop to 0. With the capacitor, it is holding and it drops slightly because the capacitor is losing charge as well. So it drops slightly, but it's not falling to 0. Where is this? What is this voltage? This voltage here is 9.5. Okay, the moment it discharges to 9.5, then the second 10 volt comes back, push it all the way up to 10 volt. Again, continue to go, it discharge. When it drops, the supply starts to drop, capacitor do the work again. It's discharging, then it flattens out the curve like this. So this is 9.7, 9.6, 9.5 again, and the supply comes back to 10 volt. This keeps on repeating as if the bottom region of the curve does not exist. If I join it here, like this. So if I highlight only this one, and this one, what graph do I get? Like this. This, VT. What is this graph? This graph is with capacitor. Rectified circuit, full wave rectification, and with capacitor smoothing. Okay, capacitor smoothing. We said that because it smoothed out the drop in the voltage. That is the work of the capacitor. When you connect it like this. This, we have a name for the voltage. We call it the envelope voltage because it looks like an envelope. Imagine like you put an envelope on top of the bumpy surface. You get something like this. That is why we call envelope voltage. And this one is very, very small. From the peak to the lowest point, how much? In our example, it's 0.5, right? From 10 drops to 9.5. So it's only 0.5. It's very, very small. That is almost like a straight line. So all this, I can just assume is like a straight line. It's like a steady current. Okay? Like a steady current. So where, if I plot from the graph, this is the middle point, the peak, right? The peak. Where does the capacitor start doing the work? From here, all the way to here. all this shaded region is where the capacitor is discharging. You can see I picked the point between 10 volt and 9.5 here. After this 9.5 volt to the 10 volt, it is increasing, right? It's increasing. From 9 to 5 goes to 10, meaning that the supply already come back. So the region here is where the capacitor is charging. Okay, so I'll put it here. Capacitor charging. It gains back all the charges. And during the yellow region, capacitor is supplying the 10 volts, so it's discharging. Discharging means it is supplying the voltage. Okay, from here to here, and this is from here to here. Same, the whole thing repeats. Here, again, the capacitor, discharge, and then the capacitor here, charge again. With the help of this circuit and a capacitor and the arrangement, and also the two diodes, we have rectified from AC current to DC current. We have changed the direction and also the magnitude into a steady current. Okay. All right, let's take 3-minute rest and then we will continue. OK， 来，我们继续啊。So 我们刚刚讲到 half wave rectification， 然后我们有 full wave。OK， 两个 circuit 我们都有用到什么 transformer。For half wave 我们用到 transformer 还有一个 diode。For full wave 我们用到一个 transformer 还有两个 diode， 对吗？然后加埋一个 capacitor。Now 有另外一种的 circuit 也可以做成 rectifier， 也是一个 rectifier circuit。And that circuit is shown on the screen here. This looks like a bridge with 4 diodes used. Now, let me explain how this works. This is also a rectifier. Is it half wave or is it full wave? This is a full wave rectifier. Okay, but without the capacitor, then the graph is like a bumpy, right? Bumpy graph like that. Okay, now how it works. Now, first, the input is AC, right? The input is AC. So whenever input is AC, we know that it changes direction every half cycle. Let's say that for the first half cycle, this is positive, this is negative. Current flow from positive to negative. So it goes here, here, here. When the current reaches here, there are 2 choices for the current. Where will it go? You see this diode is pointing in this direction. So if the current go here, that is reverse bias. So current cannot flow here. It can only choose to go to the right. So current go here, flow here, here. Again, it has 2 choices. Does it turn left or go right? Okay, again, if it goes here, then this would be reverse bias, right? So it can only choose to go to the left. Now current go here, 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 and then pass through the resistor or the load, whatever it is, and then go here, here. Now this point here is not connected. You can see if the wire is connected, then it will draw like this, like a cross, meaning that the current can flow to the left, going up, or to the right. But this one is not the same. This is the point is not connected. So it can keep on, it keeps on flowing to the right. Go up. Okay, now then the current go here, again, comes to this point, it has 2 choices again. Where will it go? You can see that the diode is both forward bias. It can go up, it's forward bias. It can also go down, that is also forward bias. But which one? This one, you have to remember what I said earlier. Current flow from high potential to low potential, meaning that it cannot take this road, because if the current take this road, then it would be flowing back to high potential. Which one is higher potential? This point, point A, and point B here. Potential at A is higher than potential at B, because current is flowing from this way. The current reaches point A first, and it comes to B later. So meaning that the current at B would have a lower potential. It cannot flow back to high potential. So it will not flow, it will not take this path. Okay, huh? So it will flow where? It will flow here. The way you understand the potential, you can think of it like a water slide. You have 2 water slides. This is from the front view. You see 2 water slides back to back, like one is just beside it. Let's say we have water slide A, and then we have water slide B. If you go up, you slide down, you go from A, you go from the top comes to the bottom, right? We can never slide from bottom to go up. No. So higher point, higher potential. So you're going from high potential to low potential at the bottom here. You take the slide number 1 slide A, you flow down higher to lower potential. You take slide B, also you flow down higher to lower potential. What if I do a bridge like this? If I do a bridge that connects slide A and slide B, horizontal, if you're sliding at A, can you go to B? Answer is cannot. Because if you're sliding down like this, how can you go horizontal suddenly? Right? 你从那边下来 high potential, low potential, 你不能经过这个 bridge 去另外一边，因为那个 bridge 是 built horizontal. If it's built horizontal, meaning that this point and this point, they have the high potential. They have the, sorry, this point and this point, they have the same potential. Same potential, no current will flow. Okay, so the bridge is horizontal, same potential. You cannot go from one to another one through the horizontal, no. Only if the bridge is like this. You see this bridge is slanted, right? 斜的。所以如果你是本身是在 B 的 slide， 你 slide 下来，你可以经过这个 bridge 去 slide A， 因为这个 point C。Point D, 哪一个比较 high potential? Point C higher potential than point D. This one, point A and point B, they both have the same potential because they are at the same height. So there is no potential difference between these two. You cannot flow there. There is no current flowing in the bridge. So that is the same analogy for the flow of current. The current cannot flow from B to A because if it flows from B to A, it's like you are flowing from lower to higher potential. It's like you are flowing from point D and then you go to C. You cannot do that. Okay? So this is cannot. The current will not take this path. It will not flow from lower to higher potential. Does it make sense? Okay, understand, huh? Now, from here, so the current will go down here. Down here, right? Down here, and then again, until this, it has one last choice, going left or going right. So current cannot flow back to higher potential, remember? So it cannot take this. No, it can only go here. So here, continue, go out into the terminal. Okay, focus only on the current flowing the load. This one. It is from right to left, right? Right to left. Okay, this is for the first half cycle. How about the second half cycle? Okay, let's try again. Let's erase this. Remember, our current in the first half cycle through the resistor is from the right to the left. Okay, let me write it down like this. To the left. This is first half cycle. Now, second half cycle changes the terminal. This is now positive, this is negative. Okay, current coming up from here, going here, going here. Where will it flow? That is obvious because this is reverse bias. So you can only go here, until here. Left or right? Go right, because this is reverse bias. So you go here, go here, go here. Again, it flows from right to left. Continue, continue, up here. Until here, where will it flow? It cannot flow back to high potential, okay? Because initially the current is passing through here and it reaches this point first, point A. Current 先到 A 先，过后它才到这一个 point。所以意思说 A 是比较大的 potential. The further the current flow, the lower the potential. So B has a lower potential and it cannot go back to A. Then it can only go to up here. Again, one last choice, right or left? Right cannot. Then it goes left. So come back, come back, come back, and then enters the negative. Where do we look? We don't care the bridge. We don't care how the bridge looks like. We don't care how the current flowing there. We only want to care how the current flow in this branch, in the branch where the load is placed. Here, I'm only interested in this branch. The rest is just the rectifying, the circuit doing the work. I only want to take these 2 points. Now, the current flowing through the load, both first half wave and second half wave, is to the left. The rest also repeat the same. All the current is flowing in one direction. This is again unidirectional. So if you connect your CRO between these 2 points, what do you see? You see the wave like all bumpy, still bumpy because you don't have a capacitor, right? You don't have a capacitor, so it's like this, and then they have the same amplitude, and they are all positive value. This is another rectifier. This is with the help of 4 diodes without a transformer. Okay, only 4 diodes, and then a bridge, like a rectangular bridge. So any devices that is powered by DC, where do I connect it? I connect it from this branch. So I branched out 2 terminal or any terminal you like. Then you connect to the circuit. That circuit will have a DC current. But this circuit here is an AC. So it's like you have AC and DC at the same time in one whole complex circuit. Okay, so you can think of it. You can think of it like this whole thing is like your charger. This whole thing is like your computer charger, the adapter. When you plug into the socket, what is coming out from the socket? AC coming out, and then it goes into the circuit of your adapter. Coming out from that adapter, it is already DC. And that current goes to the input of your laptop, or it goes to the pin of the charging pin of your handphone. Handphone charger also, if you open the charger, you look at what is inside. Inside you see this circuit. Actually, it's not this, it's the previous one. The previous one, the one with the transformer, you see, transformer and the 2 diode. Okay, yeah, that one. That one, you will find that circuit in your phone charger. It converts the AC to DC, and then your charger that goes into the phone pin is already DC. And then it can only charge the phone because rechargeable battery powered by DC. So this sums up, okay, the rectification. So everything about rectification.